So he's the founder of the University of Virginia Autonomous Racing Team, which is called the Cavalier Autonomous Racing Team. And it's famous. It was the first U.S. team to win the Indy Autonomous Challenge. That was in September of 2024. And so Madhur has, in addition to this, this kind of achievement, he also won first place in the Department of Energy Clean Tech Prize. He's won Best Paper Awards in IROS, ACC, and ICCPS. And we're delighted to invite him here to Berkeley today, where he's going to present his work with a great title, Bringing AI Up to Speed. Thank you, Madhur.
Thank you, Claire. Hello, everyone. Thanks for coming in this afternoon. I want to just jump right in, right? So the field of AI is already moving crazy fast. So then why am I here talking about bringing AI up to speed? Well, let's start with a very simple question. What would you consider is a more intelligent task, becoming a chess grandmaster or being able to drive? Now, obviously, there's no correct answer, right or wrong answer, but instinctively it feels like chess should be the obvious answer. This game requires reasoning and calculation, memory, pattern recognition, strategy, anticipation. It has all the hallmarks of human intelligence. Driving, on the other hand, is just, feels more like routine. Billions of people can do it every single day. But we can flip this around and now ask, what's more difficult for AI to solve? And you can already tell where I'm going with this, because of your intelligence, that chess has solved since decades. Right? We have a free software which can beat any grandmaster that has ever played this game, ever will play this game. But can we say the same about AI and driving? And this is sort of, in your neck of the woods, AI and driving is a real thing. You can see these cars skidding around everywhere in the Bay Area. And the answer is not quite, right? They are there, they are getting increasingly deployed, but they are also getting stuck. They just kind of routinely freeze for no apparent reason sometimes, and it seems to get better over time, but it's very unpredictable. And then they have to call home and require some sort of remote assistance. But many times I see them making the kind of mistakes that good human drivers would never make, or very less likely to make. And unfortunately, as you know, sometimes, because this is a safety-critical system, these mistakes can have very, very tragic outcomes, as we saw. This happened in recent past as well. And now it has also become clear that many of these cars, even though they are getting deployed, they require human babysitting. So, you have the human monitors or teleoperators who are sometimes just correcting the car at a behavioral level. So they will issue a command like pull over or slow down or you can make a right or skip this intersection. They can give like higher level guidance. Or worst case, they can literally kind of take over the steering wheel remotely as well. And in fact, if anything, we need more transparency and accountability on how frequently this is happening and what are the sort of situations which get resolved in this manner. But for the sake of our discussion, the dichotomy here is how come we have solved the seemingly higher intelligent task quite easily, but we are struggling with the mundane? And I trust this audience to already know the answer, but I'll just emphasize it. The part of the answer is that things like chess, they are considered to be very closed. Yes, its complexity is ginormous, but it is bounded by structure, by a finite set of rules. Driving, on the other hand, is an example of what we call an open system. And that simply means that anything can happen on the road. And so an autonomous vehicle ought to be able to deal with any kind of unexpected traffic situation, which is a very hard problem. And so, trust me, I grew up driving in India. I know a thing or two about unexpected driving situations. So more formally, we can describe this problem as a problem of coverage, where you can imagine this huge high-dimensional, indescribable space almost, where some direction in this space is encoding all the different possible objects you could ever encounter on the road. This is already very difficult to enumerate and list out. But let's say you do that. Another axis or another direction in this space is going to account for all the variation in environments. And by environments, I mean broadly, not just weather or lighting, but even the road geometry or a roundabout or urban environment or a rural environment and things like that. So this is a huge space to cover. And even if somehow you have confidence that your foundation model or whatever have you is going to do well in detecting all the different pieces that you need to detect, the next axis or the next direction is going to get you, because this is spatio-temporal interactions between all the different agents and all the different environments and how possibly they could roll out over time. So this is immensely impossible to describe. If we cannot even describe what this box looks like today. That's part of the challenge. How do we cover something which we cannot describe properly, and we therefore cannot make any guarantees or any kind of predictions of how well we will behave in different regions of the space. And so this is what roughly is happening in the AV industry. People are trying to cover little parts of this coverage space, and that's what we like to call these operational design domains. So if we are within the box, we have some statistical confidence in the kind of errors you will experience. But in the last 3 years, as is known to this crowd, we have seen some amazing progress in other open systems, like language, or more recently with computer vision. And problems which were considered almost impossible many years ago are now already solved or on the verge of at least human level or outperforming human level performance. So we have LLMs today that can basically pass these exams or do well on math problems and on vision problems. But the point of this entire talk is to kind of emphasize what motivates me is that this is not sufficient for general intelligence. And as you probably already know, what is missing from this picture is what we call physical intelligence. This is how we experience the world and understand how things interact with each other, how they roll over, how we simulate the world over time. This is sort of missing from these two modalities. And I'm going to say some fighting words, happy to take rebuttals at the end of the talk, but I would say you cannot have general intelligence until you also solve physical intelligence. And I'm reminded of this quote from Richard Feynman, what I cannot create, I do not understand. And these models today, they cannot really create realistic physical interactions because they don't understand spatiotemporal grounding and contact physics, or how to generalize 1-0 shot in a situation you haven't seen before. And it's jokingly said like gymnastics is becoming the new Turing test for video language models. And this is not to say that they don't work well. Actually, they work exceedingly well. Here's an example. These kind of clips became very famous about a month or so ago. I've muted the audio here, but these are completely AI-generated characters and video, and they are actually discussing whether they believe they are just prompts or are they more than prompts, which is, I guess, both amusing and maybe somewhat concerning at the same time. But this is hyper-realistic. This is amazing, okay? And so when you look at such demos, you can't help but agree that attention is all you need. But then also pay attention to the background. In this image, video, you will see the cyclist is just going to go through traffic. And here you see traffic is flowing in one direction, and then a bus just kind of goes in the opposite direction. And some of them are very subtle, but you will see some pedestrians, they are getting spawned in the middle of the road where high-speed traffic is flowing. I think my point is made, that we are not quite there yet just because we have scaled a lot of data, which is easily and passively available to gather. For these reasons, autonomous driving, in my opinion, is nothing but a very good ultimate kind of litmus test for physical AI. It has all the right ingredients. You have real-world complexity. You have to make decisions in real time. You have multiple modalities of sensing, just like the human embodiment. You have to reason. You have to deal with this open world. And most importantly, unlike a language model or any foundation model, here, you cannot hallucinate because safety is non-negotiable. So for these reasons, my group has focused over the last few years on trying to address some of the hardest unanswered challenges when it comes to safety of autonomous vehicles. And in the rest of the talk, I'm going to very briefly touch upon each one of them. I'm most likely just going to leave you short, wondering for more, which is great because you can ask questions at the end of the talk. But I'm going to give you the intuition behind our thinking of some of these problems, where have they led to and where they are likely going. So let's start with one of the hardest questions to answer, in my opinion. How do you measure the safety of an autonomous vehicle today? And this shouldn't even be a question, but surprisingly, there is no single correct answer. There is no agreed upon definition for what is considered as a safe autonomous vehicle. So there's no consensus for correct reasons. It's a very hard question to answer. It's so subjective. What is the benchmark you're trying to meet? And so people come up with all possible type of aggregate measures like total miles that you have driven in simulation plus real world, or how many disengagements per X number of miles, or more recently, how many traffic reports or police reports or insurance reports. You can compare that to statistical human numbers. But is this sufficient is the question, right? So I don't believe it is. Because we cannot answer questions of the form that if I had two vehicles in this huge space and they're operating in different regions, different time of day, could I answer comparative questions like what is safer? Is A safer than B? We would like to have some empirical or more objective measure of their safety rather than subjective measures. It's a very difficult question to answer, and I don't claim to have a single answer for you, so sorry if you were disappointed. But I will say that in order to answer such questions, we have to answer a separate question, which is that we need to observe them in similar traffic situations. Only then it will make for a good apples-to-apples comparison and a meaningful comparison. Okay, so this apples-to-apples problem is very simple. I have a fictional autonomous vehicle company, and we are interested in how their vehicles navigate tunnel traffic, just for the sake of argument. This may be the most difficult situation to analyze in the real world. And what we would like is, if you had other autonomous vehicle companies in the world and they had their own data corpus, we automatically want to figure out all the situations where their vehicles also experienced tunnel traffic. So then we can just look at tunnel traffic and try to say, oh, you did something else, but 50 other vehicles have done something else. Humans are in agreement with what you have done or in disagreement. You can get some sense of statistical measures of how agreeable you are with humans. That doesn't necessarily mean you are safe, but it's a step in the right direction. So what we would like is, we have this huge coverage space. We would like some kind of a embedding of this space. And this embedding needs to have some nice properties that, firstly, we could extract where you are in the space directly from your observations or your sensor data, if you are an autonomous vehicle. This embedding needs to have some notion of distance. So if you have two different points in this embedding, I can measure how close they are or how further apart they are. Distance needs to have some meaning. Maybe they are close together because they are experiencing similar traffic in similar four-way intersection. And if you have all of these properties, you can start answering these similarity questions of the apple-to-apples problem. Given this reference, find me everything similar to this. And so this is a problem we wanted to solve. This is, like the title says, we want to create this scenario to vector, similar to sentence to vector or word to vector for natural language. But this is much more difficult because it's too open world. There is no fixed grammar to operate on. And so it's extremely difficult to define what this embedding space looks like. And so our thinking has been to it has evolved over time, but initially it started with some sort of a structured scenario description language. Think of it as it's an interpretable embedding. And there is nothing unique about this example I'm showing here. There are many others, including work from Berkeley, Scenic, and Open Scenario. But eventually, all these languages or semantics, they're trying to capture something on the order of what are the different actors involved, what does the geometry of the scene look like, what are the actions that the different actors perform over the period of time. And then you can have different levels of refinement as well. You can operate at a very abstract level where you just say, well, you made a left turn, but not all left turns are equivalent. There are left merges, there's aggressive left turns, gradual left turns, so you can keep going down the scale of refinement, if you will. So this is already very rich, is the point here. And so initially, about 4 to 5 years ago, when we started thinking about this, we relied on video transformers back then to just try to see if they are any good at this task. So given some reference footage from a dashboard camera, can you automatically find out what are the similar looking examples from the entire data set over here. And so this is more than just pixel similarity, by the way. We have to pay attention to what is going on. Where are the actors? Where is the spatiotemporal similarity? And it does work, but for very simple descriptions, right? So the example I'm showing you is like a very simple example, the car is basically making forward progress unobstructed. But whenever you have some rare situation, you are not able to encode it properly into your scenario description language. And ultimately, this is happening because your transformer is also having to spend some learning capacity in solving all of perception. It needs to figure out what is perception, and then it also needs to reason about the similarity space and the description language as well. So we moved past this video transformers. Maybe we can try again with some of the latest foundation works. I've been interested in that. But why are we making a model work harder than what it has to do? Let's get rid of perception and work in trajectory space. So now we can reduce the entire interaction to just the trajectory and how every vehicle has moved in whatever lane. And we can now ask the same questions about similarity, but in this trajectory space. So we have an equivalent kind of pipeline called TAP, trajectory to action pipeline, which can automatically try to produce these scenario description embeddings from these scenarios, which are encoded in trajectory rollouts rather than the raw camera LiDAR footage. And so this also works. It suffers from another limitation that your true similarity is not just individual vehicles and how similar they are to each other in different situations, but it is some joint similarity of you and everybody else around you. In fact, everybody else around you is also a very tricky question. You actually want to just pay attention to the most critical interactions in your vicinity, not just every possible interaction. And so more recently, in our work, which is under review, we have shown that it turns out that language is a promising way to also describe this large embedding space. So if you can extract this trajectory information into just a description which is in language, and you can use the reasoning abilities of some of these large models, it can be very precisely provide you good intuition and descriptions of the different interactions, the critical interaction, the intention of the surrounding agents and the environments and other agents in the vicinity as well. So this is a kind of exciting to see that ultimately we may end up going to language. I'll take one quick question, Sanjay. Yeah.
Can you go back to the previous slide?
Yeah.
The top right.
Yeah.
Explain a little bit why the middle one is not similar and the third is similar.
So this slide is trying to show that how you compare similarity of trajectories shouldn't just be a measure of their average displacement error. So you can compare the distance between two trajectories, but in our paper, what we are trying to show is that a left turn is different from the left turn we were trying to seek. So in this example, you have an aggressive left turn followed by a straight. That's the reference action which took place. And so
is that not one flat vector?
No. So it has two kind of modalities. You have a lateral similarity and longitudinal similarity in dynamics. And so what this was trying to show is that the thing which you would return if you were to just calculate ADE is not necessarily semantically the same as your reference action. Yeah. All right. Okay, so we are trying to, like I said, solve this problem in language space as well. So you can think of this as we tried pixel space with video transformers, we tried trajectory space as well, and that is also very promising, but it suffers from how do you jointly analyze all the possible trajectories and interactions. So the scaling is an issue there. But if you can describe everything in text, there seems to be a promising way to solve that similarity problem, which itself is just a precursor to hopefully solving or addressing the safety problem, which is really what drives this research. Okay, I'm going to move past and jump.
Can I ask another question?
Please. Yeah.
So I thought that you were going to go from trajectory data or video data into the scenario description language.
Yeah.
Then measure similarity after computing some embedding. But is that not what you're doing?
No, in this work, that's precisely what is happening. But this similarity is only between ego agents at the moment, right? So, but we are not paying attention to the rollouts of all possible trajectories for every agent.
So it's like a trajectory-wise similarity.
Correct. I want like a scenario level similarity metric and not an agent level similarity metric. Yeah. Yeah. Okay, I'm going to move to a related but important question, which is it's not sufficient to do these kind of analysis and measuring tricks. We also have to have some mechanism to learn from them, learn from our failures. And so you can think about this next problem as, going back to our kind of motivation diagram, I want to cover this large space. So of course, we can rely on simulation. So we want to cover the space as realistically as possible, as much as possible in simulation, and that eases the burden of deploying it in the real world. Of course, we don't want to just cover random situations in simulation. We have to be intentional about where do we simulate. That's kind of the important question. So it would make the most sense to simulate scenarios where your autonomous vehicle will crash or where it will fail, because then you have discovered some way to patch or improve your autonomous vehicle stack. So we want to do this. We want to generate simulation scenarios which are targeted and which cause AV failures. But of course, we want to do this automatically. It shouldn't be like hand engineered, because that's, again, not going to scale well. So this is the subtopic of another dissertation in my group. And here's the high-level idea. Imagine you have a simulator. You can pick whatever you like of your choice, Calra or these box world simulators like Waymax or Freeway Environment or NVIDIA simulators. And typically what people do is they will have an ego planner or an ego agent, and they can set some kind of a simulation infrastructure to improve the agent over time. In this example, I'm showing you how you would use RL, but it doesn't necessarily have to be RL. So this is how people typically use simulation to improve the ego actions. But what we are saying is, forget about the ego vehicle. Let's say you are given a black box implementation of the ego vehicle. What we would like to control is all the other vehicles in the simulator. So all the other vehicles around the ego are the actual agents of our reinforcement learning problem, and they are getting incentivized to cause a failure to the ego vehicle. And so this is what you can call automatic falsification, because you are automatically trying to cause a crash. And if you succeed, you have sort of found a plausible scenario where the ego vehicle will fail. And if you keep doing this at scale, you can build up a library of these scenarios, and then you can go back and try to statistically improve the safety of your actual planner, because now you have a way to expose it to all these scenarios where it previously failed. So this process is called hardening. It's not a guarantee of any formal kind. It's just statistically going to harden the safety against these falsification scenarios. So this is a pretty interesting setup. It leads to a lot of interesting, rich problems. It's kind of this bi-level optimization in some sense, where falsification is trying to increase the collision rate in this very toy world problem. But then once you train this adversary to kind of cause a crash by speeding up and rear-ending you, you can also then show that the ego will over time learn that if somebody's trying to cause a rear end, I can either change a lane or maybe speed up to get out of their way. Right, so these are very kind of naive or simple, trivial examples that I am revealing right now, but we had a paper on this in AAAI earlier this year, which goes quite deep into all the different kind of modeling choices and the RL setups, which seem to work in this kind of like adversary and improvement cyclic performance. And this is just the tip of the iceberg. My current work involves around, we want to cause targeted failures. So I want to know, in my simulator, can you just cause like your specific kind of collision? Only focus on, causing side swipes. And why do we do this? Because all collisions are not equal. Right? We want collisions where the ego vehicle was kind of at fault. They have to be salient, is the right term. So you only are interested in not random collisions, but salient collisions. So how do you regularize so that your collisions are realistic but also specific? Can you cause targeted collisions? And of course, you also want to generalize to any kind of geometry, not just these freeway environments. So yeah, this is another large area of research in my group.
Next question.
Yeah.
So what is your take on crafting these objective functions versus specifying these in logic? You could specify a side swipe collision also using like a temporal logic-based formulation, right? And of course, you have a quantitative semantics for several of those logics. So what's your take on that?
Yeah, so very good question. I think the lesson we have learned so far is when you start getting into these reward designs, it's again sort of, you are imposing your structure on the problem, and that will work, and we'll find, we started that way. But then we also found that if we just left it as cause a collision, it's a very sparse reward, you can also learn the kind of collisions that you wouldn't have specified. So like we started off by specifying lateral time to collision, longitudinal time to collision, not necessarily in temporal logic, but like a continuous reward, and complemented with a sparse reward as well. But what we have seen also work well in other RL games that people train these models on, that they just need, like a win score at the end of the day. And so this game has a win score for the NPC wins if they can cause a crash. And so when we actually go into these collision-specific rewards, then I think there is no way to avoid these symbolic specifications for what a collision is. And that's naturally going to be part of the reward design for these NPCs. So for causing these specific collisions, we do have to specify some sort of a geometrical continuous reward that will incentivize you to try to, what we are seeing is that you try to creep up next to the ego and then cause a side swipe. That increases the highest chances. And again, the point is, let's say you cause that side swipe, but was that meaningful for you to figure out? Like, could the ego have done anything? And that's kind of the main question here, right? So how do we preserve saliency of these crashes? And so reward design is one, but we are also regularizing that try to cause a crash, but don't depart from like a human driven trajectory. Be realistic in how you can cause a crash. Yeah. But yeah, I think we could have a temporal reward as well. Okay, in the interest of time, I'm going to jump on to the two, and I'll do two in one. Okay? How do you drive within safety limits and handle these chaotic situations? And to motivate this, we have to roll the clock back to over 100 years ago, and when the first automobile was invented. And at the time, there was a transition from these horse-drawn carriages to horseless carriages. And there was skepticism in the minds of the public. Would you trust this engine to blow up in your face, or what is the steering wheel that you speak of? What are these brakes that you speak of? And at the time, motorsport racing really began as a way for the automotive manufacturers to convince the public about the safety of this new, unfamiliar technology. Yes, it grew into marketing and sports and all of that, but fundamentally, many of the safety features we take for granted in our vehicles today, you can trace their origin to some innovation in motorsport racing. And so let's fast forward to what is happening today, and you are no strangers that I posit that this time we are making a different transition from driver-drawn carriages to driverless carriages. So similar questions of safety have resurfaced. Would you trust this AI driver to ferry your loved ones, your kids, yourself at high speeds on freeways or in dense, chaotic urban situations? So this time, my crazy idea when I was setting up my lab in Virginia was, well, let's use autonomous racing to advance the safety of autonomous driving. And no, I'm not suggesting that we have to speed through traffic at all times in order to be safe. Maybe sometimes you do have to react fast. But surely if you can design algorithms that can demonstrate performance at high speeds, in close proximity, in these unpredictable situations, then that should translate somehow, indirectly, into better performance on the road, especially in the unexpected situations. And so this isn't as crazy as it seems. For many of you who are familiar, the entire autonomous vehicle industry, it started with a race. So I'm kind of just telling the community to go back to their roots and race more in order to improve the safety of this technology and put it to test. And I'll be the first to concede that racing and driving in Bay Area is not the same problem. They're very different. The perception, planning, control problems are very different. But here's how I want you to think about this, right? So this is what is a typical scene when you and I drive. And here you can see this vehicle on my left, this white SUV, is going to merge into my lane. People are generally going to remain in their lanes. And then with the speed sign, I can reason about how fast the flow of traffic is. Right, so we may not think about this, but these signs, the lane markings and the speed limits, who are they there for? They are designed for humans. And so they're there because they help me not just produce my own actions, but more importantly, they help me predict the actions of everybody else around me. So when you have these dense perception signs, it gives you structure. And this structure allows you to predict better. That's what happens when you drive in these sort of situations. But if you remove all this structure, if there was no longitudinal or lateral structure, then I would be kind of surprised when this SUV starts veering in front of me. Okay? So removal of structure adds ambiguity in all the other problems. And this is what racing looks like all the time. It has less structure. The perception problem is kind of simpler in some sense, but the simplicity is lost because the prediction and planning problems are immensely harder in racing. Okay? So this is why we maybe are not crazy after all for considering racing as a way to test these ideas. So this became my North Star. I wanted to answer this question. Could racing help advance safety of autonomous driving? At the time, this was kind of 2014, 2015, the field of autonomous racing wasn't really even a thing, to be honest. And I sure as hell didn't have a race car in my garage to kind of tinker with. But growing up, I was a fan of this show called Mythbusters. And one of the earliest lessons I learned as a kid in science was before you try a crazy idea, maybe just test the waters to see if the idea has any feet. So that's exactly what we ended up doing. Okay? I created a 1/10 scale autonomous race car, which I appropriately called Formula 1/10, or F1/10, because it's 1/10 Formula 1 car. So as I was graduating my way out of Penn, within like 2 weeks, we took this RC car, we slapped on some sensors, and it was doing laps around our research lab at the time. And I prepared IKEA-style instructions for anybody to buy the bill of materials and create their own F1/10 racing vehicles. And this literally, I was sat down, created the entire curriculum, and taught the entire curriculum on autonomous racing, which anyone can still go and follow at their own cadence for free online on YouTube. And sure enough, the research community embraced us. The cyber-physical systems, robotics community, they started building their own F1/10 vehicles because it's fulfilling a real need. Not everybody had access to a full-scale car for experimentation in their own labs for controlled studies.
The arena on the bottom middle, where is that?
That's in Italy. Yeah. So sure enough, I started organizing international F1/10 autonomous racing Grand Prix. Because who doesn't love the idea of these miniature cars competing again in a battle of algorithms? So thousands of students from hundreds of universities in the world have participated in our races. They still continue to do so. We have about 6 to 7 events every year. We just had our 25th race, a few months ago as well. So this grew beyond anybody's imagination, very, very impactful. But, I'm also very grounded in kind of, being real about things. This doesn't fulfill all the boxes that we were chasing with high-speed racing. So this time, in order to make progress in the physical world, we had to ironically move to the virtual world of video games. And these racing video games, they had become so realistic, real Formula 1 drivers were racing in this game in the middle of the pandemic. And so this time, my group became the first in the world to take this $60 video game and convert it into a simulator. And so you could take the images and UDP data from the game, package it into ROS, and train these AI algorithms in much more high-fidelity physics and photorealism, and then control the car through Python rather than for a human to drive. So this became a sandbox to train algorithms for this agile racing that we were trying to unlock. And so my own group has published dozens of papers on multi-agent planning and racing. Then I want to go a little into the detail of kind of how this works, what this has led to. So geek out with me for maybe 5 minutes. The first thing we tried was essentially what anybody would try. You are getting images out of the game. Let's try to just train some controller to go from images to control space. As you can imagine, this is fine. They didn't try transformers. They were not a thing back then. But the end-to-end learning, it falters because it has no ability to essentially recover. It's very anxious when it drives. So a better idea is you go from your sensor modality to trajectory. So output a trajectory and then have some kind of legacy controller follow a trajectory. So this immediately is much better, but it also is not foolproof. You will see this car is doing things that drivers will get penalized for. So you cannot cut the corner because the image kind of washed out. Everything was gray, so it didn't know what to do. And so if you think about this problem, why is the car struggling? Part of the reason is the representation of things. And that's very important as one of the key lessons. If you ask the neural network to predict hundreds of waypoints, and each waypoint is x, y, heading, acceleration, velocity, this is a bunch of multidimensional predictions. You are asking the network to predict 500 things and giving it 500 chances to fail. It's a very high-dimensional representation output space. So a key idea was that let's, instead of using raw waypoint predictions as the trajectory, let's represent it using Bezier curves. Okay, so Bezier curves, here's my Bezier curves 101 slide. They're basically these Bernstein polynomial ideas, which many of you know are well established in graphics and vision. The red curve is what you get, and this curve is fully described by all the gray dots, which are called the control points of this curve. So I can represent a continuous trajectory with very, very less amount of data. I only need the control points. Many, many years later, I will find out that Pierre Bezier, who invented these curves, invented them to shape the body panels of Renault race cars. So they were always kind of linked to racing in some sense, but we are just bringing it back. So if you replace this representation with Bezier curves, things become much more stable. And you can see this car is now zooming around Albert Park in Australia, just a very straightforward trained neural network, and it's not making the same mistakes as the dense waypoint predictions would have made. So this is promising, but it has a very big flaw. And the flaw is that it can do no better than the data it has seen, which is like a classic limitation of supervised approaches or teleoperated approaches. So we want to fix that, right? We want to race against kind of human level performance or exceed that. So here's the next clever idea, which has been the basis of a lot of recent research on this topic. Instead of just predicting one curve for the car to follow, the control points themselves are distributions. They are probabilistic curves now. So what you are learning is essentially a distribution of trajectories. And what that allows you to do is at real time, you can sample a particle from this distribution, which is a trajectory. You can score this particle for acceleration, for track bounds, for safety, and whatnot. And then you can repeat the sampling like a particle filter and until that converges, and it'll give you like the posterior optimal trajectory that you can then send to your controller. So this approach is called differential Bayesian filtering. And it turns out that it doesn't matter if you train with images, you could get rid of them, you can just train with state information. It is not tied to a particular kind of training modality. So it is very extensible. And we have leveraged that in our research to now extend this to trajectory prediction, to collision avoidance, to multi-agent planning, which I will not go too deep into, but happy to take questions later. Okay, the last part. As all of this was unraveling, constant kind of thought lingered at the back of my mind. How do we scale this up? Could we build 1/5 vehicles or go-karts so we can race against a human go-kart driven driver and an AI driver? Well, we managed to do more than just scale this up. As Claire said, we built this. Okay? This is Cavalier Autonomous Racing. It's a full-scale, fully autonomous Indy race car. It was designed and prototyped in a racing garage in Indianapolis in the middle of the pandemic, and uses the same Dallara chassis as is used in Indy Light cities, except there's no steering wheel, there's no pedal, there is no human driver because the cockpit is just jam-packed with state-of-the-art hardware for autonomous racing. So we have multiple solid-state LiDARs and radars, 6 cameras, we have a Linux machine and a very heavy GPU, and this is a gasoline-powered vehicle. It's not an electric vehicle. And so we do this, we help shape the initial design, and I tell my students basically just drop everything. We're moving to Indianapolis because it was time to find out whether all the lessons we had learned in simulation with 1/10 scale racing would hold their own in the real world. But there's no shortcuts, right? This time the task is to write the entire software stack from scratch. Okay, so we have to do a lot of testing of every single component from the low level to perception, planning, control. In fact, here's a piece of trivia. I'm possibly the first person in the world to drive this $1 million race car with an Xbox controller when we were first testing it. So this is how it came to life. Literally, this is the first time the car ran with this Joy-Con controller. And you can see the students are cheering, even though, retrospectively is not much. The car has just driven 200 yards, but this means a lot to us. Because in 2021, we went to Indianapolis Motor Speedway, the home to Indy 500 racing capital of the world. And as you can see, most autonomous vehicles on a good day, they will go the posted speed limit. But here our car is already racing at 100 miles per hour to warm up its tires. And I want to emphasize this is fully autonomous. It's not being teleoperated. We are not sending any active control signals. It's figuring out where it is on the track, where it needs to go. It knows what the race line is. That's pre-programmed, but it still has to figure out when to slow down, when to turn. It can even do some very primitive obstacle avoidance, but at freeway speeds. And when it's done, it will automatically park itself in front of our pit box. And I know when you look at this, it's impressive, but it also, you can't help but ask, this is just one car on track. It doesn't look that difficult. It's extremely difficult because, as the complexity of your software grows, it's very difficult to predict where this point of failure would arise from. So many, many different points of failures could occur. In fact, less than half the teams are able to finish the race in the very first time. And my team emerged as the fastest American team. We didn't win the competition. A team from Germany won the entire thing, but we put a respectable, 120-something miles per hour. And this gave us confidence. Can we now do it with two cars? Could we autonomously overtake each other? But you can't just show up and start racing two cars, because then you'll just end up with two crashed cars. Okay? So I'm going to reveal kind of behind the scenes, how do we prepare and how do we test so that we gain confidence that we can actually do this. So one of the first tests we will do is we will speed up autonomously to 150 miles per hour and then slam the brakes to test our stability under this high deceleration load. And so here the car will receive a radio signal to slow down from race control, and it's going to coast itself from 150 to 0 miles per hour. And I know it doesn't look that dramatic, but less dramatic is good in this case. We don't want the car to jitter or shiver when we brake. And this is basically a validation of your state estimation of your controller put together in this integrated way. And so you can go fast, you can slow down if you need to, so then you just need to start overtaking. So another test we will do is we will be on track. There is no real opponent ahead of us, as you can see, but the race car thinks there's a ghost opponent ahead of it, traveling at 100 miles per hour. So it's going to try and overtake this virtual or ghost opponent, and you will see it will veer towards the high line as it's planning its overtake, and then figure out when to speed up based on the prediction of the ghost obstacle, and then try to complete this overtake into the middle of this very banked turn. Okay, so it's a very safe way to test overtaking without necessarily putting two cars at risk. So we do this over and over at different speeds. But ultimately, you do need to open your eyes and see the opponent. Okay, and so we have this team from Germany. They are autonomously going at about 60 miles per hour, and we are just tailgating them at 40 meters to match their speed. And we have a lock on them, and we have a trajectory prediction on them. And we do this by fusing multiple modalities of sensor. I'll speed up through this because it's not really tied directly to any of the research themes, but we do use neural networks for this is my main point. It's not all classical perception. So we have this bird's eye view prediction or detection of the opponent. For radar, we have two different modalities. We use clustering-based approaches and also neural network approaches that we are transitioning to. We're in the middle of that, so that's why we have both and not just one. And then we've also trained models to detect the opponent using the cameras, of course. We have 6 of them, so we use all of them. In fact, what we will do a lot of time, we'll go to track and do runs like this. There's a very slow speed choreographed overtake where we are just following parallel lines on purpose. And the sole reason for doing these kind of data gathering runs is because you can go to the frame that your sensors collect in that data. You know where you are because of your own state estimate, and you just go across pit lane and get their GNSS data on a USB drive. So you kind of know where they were from their data. And then you know the rigid body dimensions of the opponent, and so you can label this data automatically. And so once you have this labeled, you can train your perception modalities on these synthetic labels. It saves us a lot of time. In fact, all this data is publicly released. Anybody can go and just take this data, which is labeled, has the ground truth positions. It's called the race car data, which was released many years ago. We're planning to release another set of this with more multi-agent interactions. We take all these detections, we fuse them together, and we have a single best detection of our opponent, which is from every single sensor. And then we have to do a prediction of the opponent. So we use some of the Bezier curve magic sauce there that I described to you, which is also published. And when you put all of this together, you have to pay attention to the amount of compute you have on these cars. They have a good ruggedized computer, but not a ton of CPU. So you have to be mindful. Everything runs on C++ and very, very lightweight executions. And when you do all of this, this is what you get. This is a team from MIT. They are going at about 115 miles per hour. So a car will accelerate to 130 miles per hour. We've already done this individually, but now it's put together so we can overtake them reliably. In fact, we'll keep doing this. Next time around, they're going faster, so we have to actually go up to 150 miles per hour to complete this overtake. And this is all being decided by our algorithms at runtime. In fact, let me play a little video from one of our recent races, because something very exciting happened there.
Wait till they get on the straightaway, and it looks like they're going to try to go to the high side, but that might not work, right? So they're going to have to...
Oh, that's awfully close. So close here. And Cavalier did a brilliant job of recognizing.
They really committed to that outside line, and the outside line wasn't there.
Yeah.
And so they slowed down, and actually it was amazing to see that they then slowed down, came back down the track, recognized it was a new line it needed to take, and then took that, and then made the pass look quite easy at that point, right? So that, I don't know that I've actually seen that before. So that was pretty outstanding work there by the team.
Yeah, I agree with him. It's outstanding work but this was vindication almost, because the first evidence we saw where our planner actually prevented what would have been a sure shot collision with the opponent. And this is sort of the very first glimpses of why in racing you can push something to its very limit, but also test its ability to react at those limits. And this moment like these, which are also a reminder of why racing is such a difficult test for autonomous driving. Every single part of autonomous driving is pushed to its absolute limits when it comes to racing at these high speeds, especially in the presence of other dynamic agents. Okay, let me speed up because I know we are hitting the end of time. Our next challenge was the race car basically changed into a different car. Okay, so we improved the car, but ultimately we had a different computer, different set of sensors, even a different drive-by-wire system on the car. So the question this time is that can all these algorithms, this physical intelligence or AI that you've developed, can it adapt to almost a new embodiment? The only thing which is common is the engine and the chassis. Well, no discussion about physical AI is complete, in my opinion, without physics. Right? So this is how the car operates. It doesn't matter if there is an AI driver behind the wheel or a human driver behind the wheel. At the end of the day, just like what my boy Newton has said, the car is going to move forward because of the way the rubber makes the contact with the tarmac. So we have a lot of research on how to unravel this nonlinear physics, how to adapt at runtime. These slip angles and this tire grip nonlinear models. So it's quite literally, in my world, you have to understand where the rubber meets the road in order to do well on track. Okay? There's no escaping it. So what took us 3 years to master, we had to replicate in 3 weeks across 3 different tracks. Okay? And we test for 500 miles, which is like running an entire Indy 500 by yourselves. And we leverage a lot of simulation as well, because track time is super expensive, and you will only get a few weeks of track time in an entire year. So we rely a lot on very, very high-fidelity simulation to gain confidence. We've even developed our own in-house simulators to do very quick open-loop lap simulation, strategy simulation for passing competitions. We do all of this to return to the Speedway in the fall of last year for kind of one more shot at glory, at the title. And this time, the competition is even more fierce. We have 10 teams from all over the world, 6 US teams from Germany, Italy, from Korea. And you can already see, the bar is much higher than the last time we were on this track. The average speeds are in the 160 miles per hour. And just before it's our turn to go out on track, many would recall, if you were there, it starts to rain. You don't need to be a Formula One fan to realize that racing and water doesn't mix well. Okay? And we are not a real F1 team, so we don't have special wet weather tires or some fancy tires. So all we can do is just wait for the marshals to try to clear the track. And they do take like 2 hours, 3 hours to do so. And a top team, a previous winner from Germany, they go out right before us, and they push their car to 166. And as they're pushing it further, this is what happens. Yeah. In one instant, because the margin of error is so thin, that's the difference between kind of winning and just losing your literal research lab on wheels. That's how I see this car. So it has just rained, and another team has just spun out. So what do? Right? You are going next. Do you put your faith in all the ICRA RAL papers that you have written and try to find the grip where there might be none? Or do you play it safe so that you can return and kind of race another day? Okay. I think you already know what happened, but let me play it. We sent it.
All right, let's see. They didn't need a lot. They did it! 170.645 from Cavalier Autonomous Racing in the University of Virginia. That, folks, was an amazing lap, especially after following a car that had an incident, then a stoppage, and then going out and pushing the envelope like that, Rob.
And they're still going. They're still on here, trying to get a little bit faster at 171. They crossed the yard of bricks over 180 miles an hour here as they came in front of us. So, but they're a little bit slower down the back. We'll see. They're 170 through the corner again. This one is going to be close. They're going to be really close, I think. Again, they definitely didn't stop pushing.
They're driving a beautiful pattern. This robot in the coating is driving absolutely beautiful lines.
I expect this is probably their last lap to go to time in over 181 miles an hour there as it crosses the stripe. There it is.
171.011. They just continue to open it up. What a lap. 2 laps over 170 miles an hour. They do 2 more like that. That's a 4-lap qualifying run here at Indy.
Yeah, I usually shut up when this video is playing because he's doing an amazing job of describing what is going on the track. And he's right. With this lap time, we would have been on the pole position in, I think, 1972, 73, but ahead of Mario Andretti. The beautiful thing about this is in that last corner, our AI driver is commanding 100% throttle in the middle of this turn, exactly what you would expect from the top-level human drivers to do. So my team becomes the first American team to win this challenge. We set a bunch of lap records, but on that day, at the time, we also set a world record for the fastest autonomous speed on the racetrack because we hit 184 miles per hour when we crossed the yard of bricks. I'll personally never forget this little moment from later that afternoon when my team and we got a chance to kiss the yard of bricks. It's a tradition reserved for winners at Indy. And I just have a feeling there's not many computer scientists who have gotten a chance to do this. Okay, let me try to park this car. Okay, we have mastered oval tracks in the last 3 to 4 years. So where are we going next? Okay, for us, the story has just begun. We do a lot of testing. Earlier this year, we had the opportunity to test our car at this space shuttle NASA runway at Kennedy Space Center. I think it's one of the longest straights you can get in all of North America. So you can imagine many autonomous vehicle companies also test there. So we go there to kind of unlock these physics-based models. We have to be very confident about our own predictions of how the car is going to behave. And in fact, we also demoed the same level of speeds in complete darkness. In pitch black, the car is going across the runway, something a human driver would be hesitant to do at 160 miles per hour. There's no lights around the runway or anything of that. In summer of this year, we also, as many of you would know, because the Berkeley team was also there, we are transitioning to road courses. This is a whole new level of complexity in vehicle dynamics and control and motion planning because you have to brake aggressively, steer aggressively. And Laguna Seca is not like the easiest track to choose. It's one of the actually most technical tracks in the country. It is not just windy and twisty, it's also uphill and downhill. It has a very famous corkscrew turn where there's about a 24-degree incline that you have to navigate. And so, there's a lot of complex issues at scale. We had to map the entire track using these LiDAR maps or SLAM-like techniques because on this track, you intermittently lose GPS positions. This car is going to go underneath this pedestrian walkway, and you can see it loses GPS, but you still have to kind of localize yourself. Okay, whether it's single car or multi-car racing, I personally don't think we are close to human level performance when it comes to racing. This is what human drivers can do. They can race in these chaos of 20 other opponents, and they do this every weekend. So how are they able to do this? And they have some mental model or world model to assess risk, to do the spatiotemporal prediction in this very unstructured environment. So none of the algorithms that we or others have designed are capable of doing this level of performance. But we are trying. In January of this year, we raced with 4 drivers for the very first time. I know it doesn't look as chaotic as the previous video, but this is where the future of autonomous racing is headed. I'm personally very excited about this. And I began this talk by posing a very simple question. I'll end this with just one last question. Who would you trust behind the wheels of an AI vehicle? You want an AI driver with the skill that has been collected by observing the average American driver? Or do you want an AI driver with the skill to match or possibly surpass that of some of the best drivers in the world? And so when it comes to racing, my meta goal is very literal and real. I want to create the grandmasters of artificial general driving intelligence. So we can truly bring AI up to speed, but in the physical world. Okay? Sorry for exceeding time, but I'm happy to stop here. We got some questions during the talk, but I'll be around if you have more questions. Thank you again for showing.
Yep, thank you very much for the very exciting talk. Maybe in the interest of time, we'll just have one question.
I have a question because I think the F-110s to me has more impact because it bring AI to more people, right?
Correct.
So in the F-110s, I have to be honest, I never been there.
Sure.
So my question is that in the indoor environment, you just talk about losing the track, right? So in a large scale, that the arena was pretty large scale. Do you open for every team to propose their own localization, or there is actually a localization solution for all?
No. So in F-110, we have never given some Vicon or global localization. So teams,
or Arucar markers? No markers.
no markers. So everything is standalone, and teams are generally using some kind of vision or scan matching kind of techniques to localize themselves.
Right.
Yeah.
But the problem with the track is that they all look alike.
No, we roll out these air conditioning ducts to put the walls of the track, so you can put it in any shape, but they're not identical from one race to the other. And teams can actually map the track, so many teams of the top teams, I think our previous winners from ETH Zurich, they came, they mapped the entire track, and then they can localize in that. They can also detect the opponent. What we will do is we will put a little flat panel behind every car, like a license plate, so they are more visible on the sensors of the car behind you.
I see.
But the localization is fully on board. It's not global. Yeah.
All right, thank you.
Okay, thank you. One final round of applause.
Thank you.